Okay, class, this is the with you explanation for the quantum mechanics unit 1. Okay, so before we go to the notes, short idea about what we are gonna do. So when we think about subatomic particle like electron, we can represent electron as a particle. So we can see that this electron revolve around the nucleus. But when we consider this electron in terms of a wave, so this is the figure how it represents. So this wave represents the electron that is revolving around this nucleus. So when we consider this subatomic particle in terms of a wave, then we cannot exactly say where the particle is. So in that case, the particle is being represented by a wave function. So and the particle is not simply there, but it is also revolving. So it's a traveling wave function. Now this information about a particle is being represented by a wave function psi. So we assume that all the information that we want to know about this particle that is being revolving around, it contains in this wave function psi. Now let us go to the notes. By now we already know what is a quantum mechanics and even the T-Proctor wavelength and the equation. So we will go straight with the function. So we have this wave function psi, and which is a function of r and d. R is a space and d is a time. And now when we know the value of a state function, this psi rd, for a particular value r for at a particular time d, then that specific value will represent the probability of finding the particle at that point r in time d. Okay, now to find out the nature of the wave function psi, so in order to find out the nature of the wave function psi, we will take two assumptions. And the first assumption is that the quantum mechanical particle is free. So we will assume that the particle is free, which means there is no external force acting on that particle. And the second point is that we will consider the motion of the particle as non-relativistic, and we will consider in one dimension along the x-axis. Okay, now as we are considering the particle in terms of a wave, so we will consider it as a harmonic wave, and the particle is also traveling. Now when we talk about a traveling harmonic wave, we have two type of function. One is the real harmonic wave, and another one is a complex harmonic wave. So for the real harmonic wave, it can be in terms of sine, or it can be in terms of cos. Okay, now this term minus k of x, this term is being added in the function y because the wave is traveling. So for the traveling wave, we will have this extra term which shows that the wave is traveling. Now let us test whether this real harmonic wave can fully represent the wave functions of the subatomic particle. Now we will consider this equation psi1. So we are considering this psi1, and it is in the positive x direction, so which means the wave is traveling in a positive x direction. That's why we have this minus kx. And if we consider the same equation but in the negative x direction, then this minus will become plus. Now since we are having two equations which are traveling in two opposite directions, we can combine these two equations by the superposition principle. Now you have another final function psi, which is given by psi1 plus psi1 prime. Now if you substitute psi1 and psi1 prime, we'll get this one. If we further simplify, we are going to get this equation. This is, we can take a command, and sine a minus b, sine a plus b, it can be replaced by 2 sine a and cos b. Now we are getting this equation 3. Now when we look at equation 3, at time t is equal to 0, so when the time becomes 0, this t will become 0 and sine of 0 will become 0, so the entire function will become 0. But the wave function vanishes at time t is equal to 0, which means the probability of finding the particle is 0 everywhere. So which means that if the function this psi becomes 0 at d is equal to 0, which means the probability of finding the particle in this orbit is 0, so which is not possible. which is not possible because the probability cannot be 0 since the particle is there. So in that case, we cannot use this real harmonic function. So we are going to test for the complex harmonic function. Now, this is the complex function. So psi2, so we have this function along positive x direction. That's why we have this minus, and this is the same wave function but in negative x direction. So in that case, this minus will become plus. Same way, we'll use the superposition principle to combine these two equations. So if we combine these two equations, we are going to get this one, and we will substitute their respective values, and by further simplification, we will get this one, equation 4. So what happens is that for time d is equal to 0, so when the time becomes 0, then this d will become 0, so exponent will become minus 0, but e of minus 0 is 1, so you are getting this function at for time d is equal to 0. So we see that if we consider the complex harmonic wave function, then even at time t is equal to 0, the function is not vanishing. So we can consider we can consider the complex wave function for representing the quantum wave equation. Now, since psi does not vanish everywhere and is acceptable wave function representing the moving particle, so this is a wave function that we are going to consider to represent the subatomic particle. Now, for finding out the Schrodinger equation for this wave function, we know the omega given by energy divided by the Planck constant, and we already know the k, kinetic energy, root over of 2me divided by Planck constant. Now what happens is that in equation 5, we'll try to put a value of omega and k. So we are putting a value of omega and k. Okay, so after further simplification, we are going to get this psi is equal to a, this term. Now let us try to differentiate psi, partial differential with respect to d, time. So if we differentiate this function with respect to time, then we will get this one. After further simplification, we are going to get this equation 6. All right, again, we are going to differentiate this function partially, second order differential with respect to x. So if we do that, we are going to get this equation 7. So we are getting two equations, equation 6 and equation 7. So if we multiply equation 6 by IH and equation 7 by minus of h squared 2m, then we are going to get this equation 8 we will get from equation 6, and equation 9 we will get from equation 7. So we are getting two equations, equation 8 and 9. Now from equation 8 and 9, we are getting this equation by equating, we are getting this equation. That is your equation 10. Simple simplification, okay? So equation 10 is nothing but your Schrodinger equation for free particle in one dimension.